All right. Hello. Welcome. We spent some time over the weekend grading some exams. Posted those. You can pick up your exam in my office. If you follow me right up, you can grab it. I have a lab right after this though, from 2:30 to 4:30. So other than that, you can pick it up anytime I'm in the office. Stop by. You can grab it. I was worried that this exam was a little bit harder than the first exam, but the average was actually higher. So I was pleased by that. I was especially pleased by the very large spike in scores in the 40 to 45 range. Actually, that's not 40 to 45, that's 45 to 47 and a half range. So that's quite good. A little disturbed that there seems to be maybe a second peak down here. But still the average was quite good. This gives you about a 78 average, 78 and a half average even. So I'm pretty 79 average even. So that's pretty darn good on a physics exam. So even with a secondary peak down here, I don't think anybody really is in danger of failing this class at this point. So that's good, even if everyone's on here. So I'm encouraged. Obviously, if you weren't as happy with your performance on this exam as you would like, feel free to stop by and see me. We can certainly work on some strategies moving forward. We have 2 more exams left. The first one, the next one will be, I think it's the Friday before Thanksgiving, over this thermodynamics section. We'll look and behave and feel and work pretty much the same as the first 2 did. The last one can't, obviously, because we go completely remote after Thanksgiving. I'll be sending out a survey in the next week to try to gauge get some advice and feedback about how you want those last couple weeks to go. My plan now is to do, well, I don't really have much of a plan. We'll sort of develop a plan as we move closer, but I'm interested in having your input and how we can best make that a productive learning space for what's going to be arguably the coolest part of the whole semester, where we talk about special relativity during those 2 weeks. So there's going to be some cool stuff to cover. There's going to be some interesting material to cover. And we need to think about how best we can use our time to learn the material and get the most out of it as we can. So that's that. There's any questions about exam 2 or anything? I think at this point, I haven't actually looked at all of the reflective writing. There's a new reflective writing up. There will be a new reflective writing up that we do this week. There's a new Kappa up that's due this week. But pretty much the grades that are on Canvas now are pretty much the grades that are in. So. All right, very good. Then let's move on. You might remember we were talking about at the end of class last Wednesday about how adding energy to a substance, be it a solid or liquid or gas, doesn't really matter, a substance, a volume of things, adding energy to that thing can change its temperature. And specifically how much energy you need to add to raise it by a specific temperature amount. And we introduced terms that you've probably heard before, like heat capacity and specific heat, and defining them and wrote some numbers down. And I think we left off with my apologies about how this unit's going to feel very chemistry-y, because we even introduced the mole and talked about molar specific heat, and you'll have molar specific heat things on homeworks and things. It's just we share some of these terms and concepts with chemistry. Okay. So so far we have been talking about how a Q, remember Q is our variable that defines how much energy, thermal energy we've added to a system. It is how much energy that has been added to the system through thermal processes. Typically, by placing it in contact with something that is either hotter or colder than it, we can add energy, thermal energy, or remove to it, or remove thermal energy from it. And that's both Q, just one in a positive sense and one in a negative sense. So I'm talking about how that Q can lead to a delta T, change in temperature, right? But as we have seen, there are two other parameters that are also important. Specifically, the ones we talked about before were pressure and volume. It is possible to add energy to a system and not increase its temperature if you vary these other parameters as well. So in an ideal world, the P and the V aren't really changing, and that Q is going straight into delta T, but it's possible for the P and the V to change, and that's gonna, so this is always in the absence of that C, the Q equals Cm delta T is in the absence of lots of other things changing. We can't really change the temperature without changing those other two. They are related in some fundamental ways. So we cannot even have delta T without delta P and or, put the slash in the wrong place, and or delta V. One of those two has to change. So if you change the temperature, one of those two also has to change. So we can imagine doing it too simple. We can imagine it doing any combination of ways, right? You can always change these variables and see what happens, but you can imagine doing it two simple ways, right? You can change the temperature at constant pressure, or you can change the temperature at constant volume. You actually can't do it at both. So imagine two ways, two simple ways, because there are lots of other ways you could do it. Delta T at constant pressure. In this case, as T goes up, the volume has to go up, and the pressure remains constant. This is usually what we're talking about in simple questions on the homework, right? If I have a lump of, thank you for providing me a prompt again today, Haley, a lump of material, and I heat that and I add thermal energy to that material, right? It's still sitting here in 1 atmosphere. I'm not changing the pressure of this thing because it's still bound by the 1 atmosphere pressure on all sides. It will, as we know, grow by a little bit. The volume has to increase by a little bit. If you were heating up a material that were inside a steel container, that's right. And because, well, if you're just heating up the container, it's still going to be at 1 atmosphere. But it's possible for the stuff that's inside there to expand at a larger rate than the steel. And then that's exactly a case where you wouldn't have the pressure remaining constant. That's exactly right. But for most normal things, you put something in the oven. Actually, that's not a good example. You put something on here and you heat it up by something else that's around it. The pressure isn't changing. It's the other two that are going to be changing. So for solids, for liquids, where the volume doesn't really change at all, it's the pressure usually that is staying constant. Usually, what we are talking about in homework i.e. 1 atmosphere. You could imagine, though, a situation where instead of maintaining the pressure, you maintain the volume. So in this case, the temperature will go up, the pressure has to go up, and the volume is a constant. Hard to imagine doing this for a solid, right? I can't really keep the pressure, keep the volume of this, or let's say you had a steel rod or something, How are you going to keep the volume the constant? You know it's going to grow, and increase the pressure. But it is easy. So hard to think about for a solid, hard to imagine for a solid, but you could probably come up with a scenario where it would happen. But this is easy to think about for a contained gas, for instance, inside a metal container. So we have two slightly different ways of thinking about this, or two slightly different terms. We've only talked about C. You can have heat capacity at we'll call it C sub P, is the heat capacity at constant pressure. And we'll call CV the same at constant volume. So we'll run into these. And for solids, we're almost always talking about CP. For gases, well, sometimes you have to specify both. For solids, it is usually the case, and liquids, it is usually the case that CP is about equal to CV. They don't differ by all that much, even if you were to actually do the experiment and measure them independently. Since the expansion is just very small, these things don't really expand all that much. The expansion coefficients are 10 to the negative 6, 10 to the negative 5. They're quite small. Not so for gases. CP and CV can be quite different. And it'll be interesting to see how they're related, because there's very specific ways that they're related when we get to that part of thermodynamics. Okay, stay tuned. More come on this later. I don't know why I wrote that down. You don't have to write that down. Okay, but wait, there's more. So we're talking about adding energy to a system and changing its temperature, but phase matters. And I mean matters in all the ways that I can mean matters. It's important, and we're talking about matter. Okay, it turns out that there is energy, potential energy, stored up in the phase of the material. This is potential energy tied up in changing a substance phase. For example, I'm going from a solid to a liquid. The energy that's required, so I say I had an ice cube here. The energy that's required to melt that ice cube does not go into changing its temperature. So I can add a bunch of energy to this ice cube and still have it be exactly at the freezing point of water, because until it's completely melted, if it's in an isolated system, it's not going to start changing temperature at all. And that can be confusing. The energy required to make this happen does not go into delta T. You know, I didn't do. That didn't remind me. I didn't do my top hat attendance thing. Apologies. (8450) if you're in class. We might get to another question today, actually. So here's a phase diagram. Again, remember, there is a point at which solid and liquid and gaseous vaporized water can coexist at the same temperature without actually exchanging in thermodynamic equilibrium. So at the boundaries, so even not at the triple point, at the boundaries, so the water-ice boundary, even at 1 atmosphere, water and ice can coexist with each other in thermal equilibrium. If you have a really good thermos and you fill your water, fill it with water and ice at the beginning of the day, you can come back hours later, and what do you still have in there? You still have water and ice, because they can coexist perfectly happily together in thermal equilibrium. If you add energy to the system, some of that ice will melt. If you remove energy from that system, some of the water will begin to freeze. But if you don't let any energy in or out, any Q in or out, that water and that ice are perfectly happy to coexist at the same temperature in thermal equilibrium. You look confused, Bailey. Okay. This is kind of counterintuitive, right? We kind of expect it to not be able to exist in thermal equilibrium. We expect if we have water and ice that it will either be melting or it will be freezing, but that's not necessarily the case. That is not the case at all. If you do not add or remove any energy from the system and everything's at thermal equilibrium, the amount of ice or water in the system won't change. It can't. It takes energy in to melt some of that ice, or it takes moving energy to freeze some of that water. If no Q is coming in or out, the amount of water or ice in that system will not change. It can't. Okay. It takes energy to cross over. So how much energy does it take? There's a formula for that. Woohoo! The formula is this: Q equals plus or minus, and this is where it gets confusing, FML. It's the FML equation. Everybody's actually favorite equation of Analyte 3, the FML equation. So let's define all of these terms. Q, we already know, we've defined it, is the energy added, the thermal energy added or removed if it's positive, it's negative if it's removed. At constant pressure and temperature. F is the fraction of the sample that is transformed. So if I have an ice cube sitting on the table and I just let it all melt, F is going to be 1 for that particular sample because all of it is melted. M is the mass of the sample. And L has a specific name. Anybody know what the name of L is?
Yeah, the heat of transformation.
Close. The guess was heat of transformation. The L is actually a hint. That could be another name for this. But in this class, we're going to call it the latent heat. Which kind of makes sense. This is, if you've got a liquid, say a pool of water, right? There is some energy associated with that just being in the liquid phase. And if you want to cool it to below freezing, you have to remove all of that heat without losing any of the temperature to go from 1 degree Celsius to -1 degree Celsius. You have to melt all of that ice. It's like latent heat that's tied up in this substance that doesn't go into changing the temperature. Or if you want to think the other way, it's latent heat that you have to add without raising the temperature if you want to take it from a solid to a liquid state. This is a function of pressure and temperature, but usually will be over small temperature ranges. It doesn't change much. Well, and over large, we'll usually be thinking about it as a single pressure. So, right, what do I mean by that even? Here is this diagram again. Again, the latent heat obviously only is a thing at these boundary layers. If you're not at a boundary layer, L isn't even really a thing. But as you can see, for some of these, the temperature and pressure at which that transition happens can vary by a lot. So usually when we talk about an L, we're talking about an atmospheric pressure, but it can change by quite a bit if we go to somewhere else on this diagram, just so you know. We won't really be thinking about that much. What are the units of latent heat?
Joules per kilogram?
Yes, I had it both on Zoom and not on Zoom. It has to be joules per kilogram, right? Because you've got an energy on this side, you're gonna need energy on this side. F doesn't have any units at all. It's just a fraction. And M is the only other thing that you have to cancel out. So L has to have energy units to cancel out here and per kilogram to cancel that out. Precisely. Okay, there's a table in the textbook that lists a bunch of L's at atmospheric pressure. I'm gonna list a couple of them here because they're important to just look at. So let's, okay, thank you everybody for replying to this. You can go away now. Okay, so let's think about temperature for melting. Let's think about melting. And really by melting and freezing is the same thing. It's the same latent heat whether you're going in one direction or the other, except backwards, except opposite. So this is also freezing. And the other one's gonna be boiling or condensing. Column A is the transition between solid and liquid. Column B is the transition between liquid and gas. Okay, so we're gonna have, see if I can drag this down. Ooh, I can, that's exciting. Because I forgot to put one thing here. I have a temperature at which this happens, and I have a latent heat. Okay, and now what am I thinking about? How about for water? Temperature at which water freezes and or melts. Obviously it's 0 degrees Celsius, but in our preferred unit, it's 273 Kelvin. And the latent heat of water is 333 kilojoules per kilogram. Kilojoules, we're talking about thousands of joules now per kilogram. The boiling point is 373 Kelvin. The latent heat there is 2,256 kilojoules per kilogram. Two megajoules per kilogram. It takes 2 million, think about this. So what does that mean? You have a kilogram of water sitting, I don't know, in a pot that you're boiling your pasta in, say. It takes 2 million joules of energy to completely boil away that water. You wanna know why it takes you a long time to boil away a lot of water? It takes a heck of a lot of energy to boil away a lot of water, because it takes a lot of energy to make that transition. All right, how about oxygen? I don't know why I'm doing these three, but it shows some drastic differences both in the temperatures. Obviously, oxygen at room temperature is a gas. But if you freeze it down far enough, it becomes a liquid. And if you freeze it even further, it becomes a solid. That happens at 55 Kelvin. You have to get pretty darn cold to get to solid oxygen. but it doesn't take much energy to freeze it once you get it down there. It's only 13.9 kilojoules per kilogram. It condenses at 90 K and 213. The units are the same all the way down on all of them. Lead melts at 601 Kelvin, 23.2. It boils. Probably never thought about boiling lead before. You have to get pretty hot, but not ridiculously hot. 2017 Kelvin, 858 kilojoules per kilogram. So once again, water is at the high end of the amount of energy it takes to change its behavior. On the very high end of almost anything else we'd look at. Okay, so here is a concept question for you that I want you to think about. Pull out your top hat enabled device. I have 1 kilogram of ice at 273 Kelvin. It's right at 0 degrees Celsius. I add 333 kilojoules of energy and let it come to equilibrium. 333 kilojoules per kilogram is the latent heat of ice. So what happens? Does the ice completely melt and the temperature rise? Does the ice completely melt and stay at temperature 0 degrees? Does the ice partially melt and the temperature rise? Does the ice partially melt and the temperature stay at 0 degrees Celsius? What happens to ice? Question mark, you've got 4 choices, go. Again, this is all for fun, none of this counts. Except your own competitive spirit should be intent on getting this one right. Feel free, I guess nobody's really close enough to talk about it. Normally I encourage my classes to talk about these things. This is all for fun anyway, but we're all socially distanced. One of the other things, just another thing we've lost this semester, sadly. 20 seconds left. Yes, Isaac. Yes. That's right. Those are specifically at 1 atmosphere, and they can change if the pressure is different. That's right. 4 seconds left. All right, let's see what we got. Oh, B is by far the choice, although A, C, and D both got some love. Let's anybody want to take a stab at arguing for one of these? I'd be impressed if somebody argues A, C, or D. Go ahead. Go for it. Argue B.
Okay. I guess this would be in like a perfect system where you don't have to worry about the air heating up or anything like that.
Right. Totally isolated. Yep. No other energy around.
So since you're adding 333 kilojoules energy
Okay, so the argument is that all the energy has gone into melting it, and therefore none of it can go into the changing of the temperature itself. Since that is exactly the latent heat of water. We want to argue for A, C, or D. Nobody bold enough to stand out on a very narrow limb by themselves.
Nobody bold enough to stand out for the wrong answer.
Precisely. So that's right. So good job there. Let's think about all these in turn, right? If we had added 335 kilojoules of energy, what would happen? It would all melt and then start raising in temperature. If we had only added 330 kilojoules of energy, what would have happened? It wouldn't quite have all melted. And what would the final temperature be? Still has to be 0 degrees Celsius. There is no, C cannot happen in thermal equilibrium. There's only a single temperature at 1 atmosphere where water and ice can exist in thermal equilibrium, and that is at the freezing point of water. They cannot coexist in thermal equilibrium at 10 Celsius. You can put an ice cube into water at 10 Celsius, but if you wait long enough, what's going to happen? The water will cool down, and what will happen to the ice? The ice actually can't warm up until it melts, right? Ice cannot be at 1 atmosphere. Solid water cannot be any hotter than 0 degrees Celsius. And water, liquid water, cannot be any colder than 0, right? So that's, again, something you have to wrap your head around and have conceptually down. Those are specific boundaries. You can introduce a ice cube that's at negative 10 C to a glass of water that's at 20 degrees Celsius. But when you put those two things in equilibrium, they're not in equilibrium when you put them together, right? Energy will be transferred from the warmer water to the colder ice. First, to change their temperatures, and then to begin to change their phase. In the end, you might have some solid liquid combination, but if so, it has to be at 0 degrees Celsius. You might have all of it melted, in which case you can be more than 0 degrees. You can have it all freeze, in which case it can be less than 0 degrees, but you can't have in equilibrium water and ice coexisting at any temperature other than 0. And the same with steam and liquid at any temperature other than 100 at atmospheric pressure. Okay. All right, good. The other thing you need to do is worry about signs. L is always positive. So, positive Q is required to go from solid to liquid to gas. Negative Q is required to go from gas to liquid to solid. So let's do an example. You have a 100-watt microwave. This is just going to be a, no, it's not. 100-watt microwave runs for 5 minutes with a half a kilogram of water. Initially at 40 degrees Celsius. It's pretty hot. Probably doesn't come out of the tap water that hot. You probably already heated this on a stove or something. Anyway, it doesn't really matter. So, do we know? So, we're going to have to think about two things. We know we're adding energy, right? The microwave oven, that's what the microwave is doing. It's adding thermal energy to our system. We could calculate how much, right? 100 watts times 5 minutes. That's going to give us 5 times 60 is 300. 300 times 1,000 is going to give us in joules the Q that we've added to our system, right? So what we don't know is we know what's going to happen, right? That Q will go into changing the temperature of the water until it reaches 100. Once it reaches 100, it's going to start boiling the water. Once it's boiled all the water, it's going to start raising the temperature of the water vapor that's inside the microwave. We don't know where it ends up. The equation that we're going to use is going to be dependent on where it ends up. We have to just guess. Let's say to start, and then the answer will tell us whether we've guessed right and have to make a different guess, right? So let's think about, what if all of that goes into changing the temperature of the water? If we calculate the change in temperature of the water and it turns out the temperature is higher than 100, we know we've guessed wrong. And then we have to add something to our equation. Well, it's going to add temperature until it gets to 100, and then it's going to start boiling it. If we take that equation and our F comes out to be more than 1, then we know we're still wrong. And we have, in fact, boiled it all and then started to, the rest of the energy then has to go into changing the temperature of the steam. So this often is a trial and error kind of problem. To make a guess about what's going to happen. If your F is negative or over 1, it doesn't work. If your temperature has crossed a freezing or boiling point that you haven't taken into consideration, you have done it wrong. You just have to adjust your equations to add the appropriate terms or subtract the appropriate terms until it comes out to make sense. So, let's try for this problem, just changing the temperature and see what happens. So our first try is just change temperature. What is our formula in that case? Well, we know that delta T, well, let's write down our original equation. Q equals Cm delta T. So delta T, we know what Q is. We know what C is. C of water is 4184 joules per kilogram Kelvin. So we can solve this for delta T. Delta T is Q over Cm. So this is 300 kilojoules. Okay, let's figure out what Q is first. I'm writing it down before I've even calculated it. We know that Q is the added is going to be the power times the time. That power we know is 1,000 watts times 5 minutes times 5 minutes times 60 seconds per minute. I do all that together and I get 300,000 or 300 kilojoules of energy. Great. So that's my Q. You can plug that in, 300 kilojoules divided by 441.84 joules per kilogram Kelvin times 0.5 kilograms. And I get 143 Kelvin. That's the delta T. That's not Celsius. That's the delta T. So if I have to add that then to my original temperature to get my final temperature, which would end up being 203 Kelvin. So we have guessed wrong. This is an unphysical thing to have happened because a lot of that energy that went into making this temperature change has to go into boiling the liquid instead. Question? Yes, yes, yes. Whenever you're doing so the question is, we're doing a problem like this on the homework or an exam, you will know what the relevant phase transition points are for the material that you're talking about. Yes. So that doesn't work. Have to try again. Okay, trial 2. So we heat it to boiling, and then the rest of that Q has to go into changing the phase. Okay, we know that. So I can add these two equations now. I know this is going to be Cm delta T plus FML, right? So some of that is going to go into changing the temperature, and some of that is going to melting the thing now. What am I solving for now? I'm solving for F. I want to know if all of this has been boiled away. Do I know everything else? Do I know what delta T is now? I do. I know what delta T is now because I know exactly where it's going to start boiling away. I know that that's going to be 60 Kelvin to get to the boiling point, and then the rest of that energy is going to go into melting or boiling my sample. Now we know, we didn't know what delta T was before. We know what delta T is now. We know the delta T, well, delta T is T initial, T final minus T initial. And we know that T final is 100 Kelvin now, or 100 degrees Celsius. So delta T is 60 degrees Celsius, which is equal to 60 Kelvin because it's a delta. So we can solve this for F. If you do that, again, do this symbolically always. F equals 1 over ml times Q minus Cm delta T. Plugging all this in, we get Q is 300 kilojoules minus 0.5. Oh, I forgot the C. Plug those numbers in. You don't really need to see me write all this out. I guess I will one more time. 4184 joules per kilogram times Kelvin times 0.5 kilograms times 60 Kelvin. All of that divided by ml, 0.5 kilograms times L of water of steam, which is 2256 kilojoules per kilogram. Plug all that in, and what do you get? Oh, well, okay. I actually simplified this. On top, I get 174.48 kilojoules. And on the bottom, I get 1128 kilojoules. And all of that is 0.155. Is that it? Are we done? We cannot be more than one. If it's more than one, then that would have implied, let's say we got 2, right? We can't boil twice as much as it's there. You can't have a fraction over 1. So if that had been the case, then all of it, we would have had to do this again. We would have had to have set F to 1 and then add another Cm delta T to see how much more, how much hotter that steam got. But this is a number, yeah, Dan, oh. In this particular case, F is 0.15. What does that mean? That is the fraction of water that has boiled from our original sample. We got a number between 0 and 1, we can stop. So we know the final temperature of our sample. What is the final temperature of our sample? 100 degrees Celsius. And we know how much water is still left. 85% or so of our original sample. And that's 15% has been boiled away. We can stop. If this number had been bigger than 1, I'll put a big check here. If it had been bigger than 1, then you need to go try a third step, which would have been Q equals Cm delta T plus FML plus Cm delta T again. Except we know what this delta T is. That's going to be 60 again. And we know what this F is going to be now, which is what? It's going to be 1. And this is going to give us our new final temperature. Using, this is going to be C of steam instead of the C of water. So again, usually these questions will be something like, what is the final temperature of the sample and how much water is left? Right? You don't know the answer to any of those questions until you start plugging numbers in and seeing how it actually works. So those are the 3 possibilities of going through a single phase transition. If we had started this at ice though, you can imagine you go through these same exact procedures to see if it's all melted, and then you have to do it again to see if it's gone to boiling point. You could have up to 5 terms here for changing temperatures, going through a transition, changing temperature again, going through another transition, and then changing temperature again. You might have up to 5 different possibilities of what actually where it's going to stop. Right. Right. The energy that we provided wasn't close to enough energy to boil the sample, even if it had started at 100 degrees. That's right. Not really. I mean, if you can do in your head how much energy it's going to take to get to 100 degrees, then you can sort of figure out if it's going to get there or not. But no, you sort of have to just try it, see what happens. Okay, so let's try passing all the way through a phase transition. If the substance changes temperature and the phase changes, you must keep track of both separately. So, for instance, if we had started where we did, let's say we started ice at negative 20 degrees Celsius, we have to change that temperature first. We have to go through that phase change second, and then we have to continue changing that temperature later. So, example, water, this is going the other direction, but it doesn't really matter. Water cools, freezes, cools more. This is identical to ice warms, melts, warms more. The only thing that's going to be different, the equation is going to be the same. C water, M delta T, plus ML, I know that F is 1, plus C ice, M delta T2. These are different delta T's. One is how much temperature it takes to bring it down to freezing point. This term is how much energy it takes to melt the whole thing. And then whatever's left goes into cooling the sample more. Note, all of the water freezes. So F equals 1. Right. This is important. I actually messed this up. That can't be a plus. This is where the sign on the FML term matters. This has to be a negative sign, right? Q is going to be negative in this case. If I'm cooling a substance that starts at water and goes to solid, Q has to be negative. These terms will be negative also. Why will these be negative? Because it's delta T will be negative. Delta T is always final minus initial. If final is lower than initial, then delta T is going to be negative. This is where it's going to get confusing. This ML term, the negative sign comes whether your change is whether Q is positive or negative. If you're going from solid to liquid, that FML term is positive. If you're going in the other direction, that FML term has to be negative. But L doesn't change. You could think of it as the F changing, and that's not a bad way to think about it, right? F is the amount of fraction of it that's going to a higher energy state. If the entire thing is freezing, that's an F of -1. But that sign does change depending on whether you're going in the positive Q direction or the negative Q direction. Just a warning. Okay, I'm out of time. We'll do another example at the beginning of class on Wednesday. Yeah, it does. That's right. Yeah, we don't have to worry about that much at atmospheric temperature, but that's right. It's the same. You can do an L of sublimation for water, depending on what the pressure happens to be. Yep. Yeah. That's right. That's right. It would be a sublimation, and you'd only have one possible transition at atmospheric pressure. That's right. Hey. Yeah, good question. Plasmas. Let me end my Zoom session real quick.